All right, here we go. I'm in my room now. I got a new whiteboard up and going. This is also my it's on the side of my house. It's a little bit cold, and it was cold last night, and I've got to move some things around and try stuff out. So as we're going through this and figuring out where things are and what's going on, let me see if this works. I'm stepping forward and you can't see my face. That kind of didn't work. I got sticks. Let's see if this makes us look better. All right. Nothing. Lighting. Oh, that looks much better. Okay, here we go with AP Physics. If you were able to watch the College Board video today, you can see that we are very much in a what the heck is going on, trying to figure it out as we're rolling. So this is you've got to be flexible. You've got to be willing to kind of roll with stuff, and yeah, that's where you go. And hopefully your entire class in my class has set you up for that, because that is a very physics thing to do. You don't know what the answer is, but you're going to have to explain yourself on how to get there. Annabelle's question is, I'm currently trying to upload my files to the coronavirus exam. We're going to get to that in a second. First thing is, remember, don't panic. If you've watched Hitchhiker's Guide, or you've been here, this is we're all in the same boat. We're all trying to figure this out as we go along. What does that mean for colleges? What does that mean for summer programs? What does that mean for any kind of stuff? What does this mean for this light that won't stay where I put it? What does that mean for all kinds of stuff? Don't know. We'll figure it out as we get along. It's not going to be terrible. So just, the entire world is in this. It's not just what's happening. So kind of stay flexible and stay positive. Know that we're all just trying to figure this out. I do know that there's some, I can't quite tell you what's happening yet, but you'll find out probably today, tomorrow at the latest, on how our class is going to work, how the district is going to work some things. And so that is coming down the pike. I'm sure probably the email will come out this afternoon. So, all right. Thank you, Ariba. I picked this beanie today because it matches my shirt and my tie. Okay. William says, I don't think we should be positive with COVID-19. That is true. Think uplifting. Think, I don't know. The joke will be coming down there in a little bit. Okay, next. Do I actually need to submit my stuff to the College Board? That's a question that kind of came in too. Not so much. I really this is the best way for me to put this out there. Well, how did it all of a sudden get dark? There we go. The questions on College Board are just an easier way for me to get it to you. That way I don't have to print any copies. I don't have to do that. So if you're having problems submitting it, don't worry about it. Try to take a picture of it, write it down, scan it in. I don't know, something of similar to that. Here we go. I think it's when it's that light right there that's giving me problems. Okay. What else? That you'll be able to, because really at this point, it's you being able to solve the problems and work yourself through it. So let me see if I can get that one off. That's this one. Yeah. That got worse. something like that, something like that, something like that. Maybe we'll go like that. We'll try that out. That's a little bit better. Yes, if you didn't see my bread making from the other day, that's totally worth it too. Other question we ran into. Oh, so we will also have some website problems. This is what's really been really nice about having website set up. I'll be able to post some review questions, some other problems to work through, and some of the things that we're working on. Gritar's question, are we going to be doing distance learning from next week? I officially can't tell you anything. It'll come down later today or tomorrow. So, okay. Also, things that I noticed watching the AP. Yeah, those questions again. The AP YouTube video from yesterday, from this morning, was that all physics teachers are weird. You'll notice that he had his jacket on, he had his tie, he had his little stickers, his pens in his pocket. Although I was expecting more of a pocket protector and some bad puns as well. So we're all pretty much the same. I had to read about his AP video was amusing. Yeah, that was pretty something else. Was anybody able to submit files for question 3? Yeah, there were some issues that are on there. Just I'm I'm not going to check to see if how it was submitted in there. I think that's right now it's gonna be too much of a challenge. I might have you submit it in through School Loop or not. I don't know. We'll see how it goes. We've got some other things coming down, trying to figure this out. I do know. Yeah. So stay connected on School Loop, and we will go from there. Can we access the old website questions? You should be able to. You may not be able to turn them on, but or submit them again, but you should be able to view them. All right. With that, let's start question number 1. Or is there anything else up here? Oh, some of the things that I thought were important coming from that video from the AP questions was the idea of semi-quantitative reasoning. The idea of that you're not going to get a problem that has a numerical answer. I think he kept using vanishingly small amounts going into that. So what's going to happen is you're going to get a problem, and then they will kind of walk you through it and then say, this is the new change. This is different. This piece is now different. So some sort of like, what if we have the acceleration, or today's problem, first one where what if it's not a square and it's a ball? How does it change? And I liked one of the things that he did. Did I have it on here? Where he called it the factor of change question. So we'll do something like that where you just solve it in variable form and then give all the constants a value of 1 and then make the one thing that changed to whatever value it is. And that'll tell you how things change, whether they're doubles, halves, goes as root 2 or root 1/2. So, all right. And then the other thing I really liked was that when he mentioned that when we say explain and describe, he is very specific and he says use subjects and verbs and stay away. My garbage can. Woo-hoo. This garbage can is older than you. Use subject and verbs and specific subject and verbs, not it. It does, right? And then when you're writing your paragraph form, you're going to ask for a paragraph length response. You're going to want multiple sentences, 5. Actually said 5 for those of you who are trying to figure this out. 5 sentences with subjects and verbs. Let's see if this helps. Ooh, so let some sunlight in, get a little blue on there. That's nice. Woohoo! Yeah, I also replaced my bulbs up there with some LEDs. They're a little bit brighter, but the spectrum is a little bit narrower. So actually, it's a lot bit narrower. All right, here we go. Yeah, da, 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 da. This whiteboard was the one that was on the back of my room up against the back. And I was able to kind of get it in here. I got it from a bank that was moving, so I'm pretty excited about that. So the first question, we have a plunger, so I'm still trying to figure out where my edges are. And then this goes all the way. Wow. Almost use the whole thing. This is going to be nice. So we have our plunger that's moving this horizontal block number 1. All right, and then this is at A, B, C. This needs to go farther over. D and E. The respectively C to D is a rough surface. These are smooth. Remember, smooth means frictionless. Not zero. All right, what's the questions here? Can I have a recipe for no-knead bread? All right, here we go. Thank you, Ariba. There is a point F. F is out here, and there's a second block at E. And so our question is, okay, block 1 is pushed with a constant horizontal force from A to B with the plunger. So here, from here to here, the plunger pushes it. And then from at B, it's, excuse me, loses contact with the block, so there's no forces on it here. And then continues to the right along the horizontal sphere, hits the rough patch, coasts for a while, no friction, slams into number 2. And they stick. All right. So we got, I don't know, something sticky. Sticky stuff. Gross. All right. Stuck onto there. And now we need to have a graph. Speed of the center of mass. Ooh, interesting. All right. So this is going to be a speed, not velocity. 0. Oh, this is time. Time A. This is really interesting too. Time B. Time C. Time D. Time E. Time F. Let's see how that looks. That looks all right. This gets the speed, the center of mass, the two-block system as a function of time. All right, here we go. Well, I would approach this by looking at as it's speeding up. So I'm going to really look at it from terms of the acceleration. So the sum of the forces are going to equal MA. So the slopes of these lines, my acceleration is velocity over time. So once I kind of can figure out what my accelerations are, I'm going to know what my slopes are going to be. So over here from A to B, I have the force of the plunger, pushing it that way, pushing it to the right. What's my speed? So I'm going to make it constantly moving this way. I'm going to make positive. So from A to B, it's going to be increasing. The speed is going to be increasing. So I'm going to have a nice slope. Where it is. All right. I found an old straight edge in my garage. Oh, where is it? Where is it? It is an old ruler. That's an old yardstick. This yardstick is older than me. Anything else? Yeah. All right. So yeah, this was way before the U.S. went metric. So here we go. So I need at time B, that's going to be the time at the end of the force. That's going to be my maximum someplace up here. And so the slope is going to be up. And I missed it. Close enough. All right. So then from B to C, there's no friction. I'm sorry, we should also have the force of gravity pulling down and the normal force coming up. However, in the horizontal direction, that's really what this is. This is the velocity in the x direction. There's a normal force and there's a force of gravity, but that's all that there is. There's no other forces on there. Some of the forces are zero. Acceleration needs to be zero, so the slope of the line needs to be zero. So from B to C, and it needs to be horizontal. From C to D, there's my normal force and my force of gravity. So friction is pulling it back. It's the only force in that horizontal direction. So that means I need to be, that's in the negative direction. My slope needs to be negative, but it doesn't stop. So when it leaves D, it still has some speed. And it's going to come down to some speed. I'll pick, just as long as it's not zero, I'm going to pick right about here. All right. The slopes do not have to match. Could they match? Yes. Does it matter? No. Do I know if they match? No. You know that I have a box full of mason jars underneath it. I'm trying not to trip over. Next. Now I have this collision at D. No. Oh, I went from D. Okay. I'm only at D. I got ahead of myself. The collision happens at E. So then from here to here, my free body diagram looks like back to and force of gravity. There's no, it looks exactly the same as from B to C. That is, my acceleration is 0. I need to have 0 slope. So it's horizontal. The slope is 0. And now we have a collision that happens at the end. The question, so we have a collision that happens. Block number 1 slows down, block number 2 speeds up. And this goes back to making sure that you read the questions. So the question is, does not ask what is the speed of block number 1. It's the speed of the block of the system. It's the speed of the center of mass of the system. So during this collision, when block number 1 slams into block number 2, the center of mass of the system, which, so the center of mass right here would be, here, as it's moving along and you get this collision, then they both, the momentum, because there's no friction here, the momentum is conserved. So the center of mass of the system does not change its speed. So this part was tricky. It stays the same speed. Questions on that? Questions about how we got into that before I move along? And take a deep breath. All right. Apparently, just to let you know how things are adjusting and moving along, there's an email that also just went out too. We'll see what happens. We'll see where things are going. All right, so let's go back a little bit. So Rushiel, so it doesn't slow down after hitting block 2. This is a speed versus time of the center of mass. If we look at, actually, let's draw the other graph then. The block 1 and then block 2. At these same times. Yeah. So the speed V, I'm going to call this V max. Max. I'm going to put V max here and put V max here. And this is V max of the center of mass system. So notice that here the center of mass, 1, 2, 3, 4, the center of mass is right here. And so this is the thing that's moving along up into there. So as this starts to move, it covers half the distance in the same amount of time. So block 1, when it comes off, must end up having at twice the speed. The center of mass is moving twice this. Center of mass is moving half the speed of block 1. So that means I need to be way up here. This needs to be 2v max at this point. Block 2 is still 0. Again, once it hits that smooth patch from B to C, let's see, was there? Didn't quite why there's no velocity change from B to C. There is no friction. We're disregarding air friction, and it's so small. There's not a lot going on there. So from B to C, that's also 0. That's a terrible looking 0. All right. Now we slow down from C to D. That's also going to slow down. That needs to be at needs to slow down steeper. Whatever that arrow turns out to be. All right. 2 still not moving. And then from D to E. Yeah. D to E. Still not moving. And then at E, you have this collision that happens. We know what the relative masses of the two of them are. Please say they're the same. Because that makes everything a whole lot easier. Identical blocks. So, do you have a collision where it's an inelastic collision? So the I'm gonna have to knock that one out. So from E to F, M1 V1 plus M2 V2 before has got to equal M1 V1 plus M2 V2 after. That's 0, M1, V1 equals M1, M2, all the M's are the same. So M1, V1 equals 2M, V1. This 2, so V2 is half of V1. Okay, nice. So whatever this turns into be, I need to end up halfway there, and that has to be at there. So now, what about that transition and when it happens? Unless you are told specifically how long the collision takes, just assume it's instantaneous. Yes, it curves a little bit there, and then it curves a little bit there. Yeah, it curves a little bit there, and it curves a little bit there. But that's generally it. All right. So back to reading the question. This is the center of mass. This is what's happening for each individual block. And you can see that these two summed together should give you this. Is that right? No, because that's velocities. Never mind. Don't say that. With that. That gets us all the way through there. Nice. And then you're going to get this classic physics wrench thrown at you, which is, now that you know all of that, make it a sphere. Take everything you just know and replace it. So, same setup. So here's my block. Here's my plunger. Now I have a sphere. I think the sphere should not be black. Let's make it blue. With a little bit of shading in it. Look at that. All right. Did you the College Board guy also made noises when he was playing with stuff? Any questions going on? My South block. Do. Because my system up. All right. So Gabby's question, because they stick, momentum is conserved not because they stick. Momentum is served because there's no external in this. So what changes momentum is external impulses. So this is so much better than the calc live stream. That's right. What changes momentum is the external impulses. Over here, there are no external impulses. So in this collision, there are forces that are happening between the two blocks, but they are internal to the system. So they don't change the momentum of the system. Does that help explain that? With that. Okay, now let's not make it a sliding block. Let's give it a little bit. Let's step it up a notch. With the let's make it spin. All right. So the plunge is returned, and now I've got a sphere. Sphere loses contact with the plunger at point B. Same thing, right? So we've got all the same setup. So we've got it's getting pushed from A to B. My guess is that it's rolling here. So this little plunger here has no friction. Going to C, D, there's that rough patch again. E, oh, but there's not another boulder rolling. Oh, you guys got an easy one. Blah. Do you have them both? Oh, you guys are talking about other things. Calculus. Okay. What's happening here? So does the sphere's angular momentum about its center of mass changes? Okay, it continues across from Rosetta. So I've got to go from A. So we're looking for the change. Looking for the change in angular momentum. So the change in angular momentum, that's got to be angular impulses. So that is, let's see, the definition of L is R cross P. Let me check my sheet. Let me see what you guys have. Oh, so it's right here. So you can almost see it. What changes angular momentum is torque delta T. All right, because I'm also a little bit loopy in here. It's starting to warm up in here. Yeah, if this keeps cool, I guess I'm gonna have different hats every day. So I'm going to be looking for any torques that are on there. Right, that's going to cause my change in angular momentum. So when this thing gets pushed from A to B, oh, I need to read that again. So because I have to look at what are the torques that are on my ball right here. So this is pushing right on the center of mass. And if this is frictionless, this ball, the forces that are on the ball, you're going to have the force of the plunger, you're going to have the normal force, and you're going to have the force of gravity. And that's my free body diagram. But I want to look at, in order for me to look at the change of angular momentum, I need to make sure that there is a torque on it somewhere. So I'm going to look at my torque diagram. So if this thing's going to rotate, here's my center of mass. It's going to free rotation around there, there. The sum of my torques are 0. So I'm going to say there's no so no torque here. This was a bad assumption. So if that's still true, it's not rolling because that's being pushed in the middle. So the sum of my torques here are 0. So this is sliding from here to here. The sum of my torques here, oops, that's a terrible torque. Some of my torques here are 0 to 0. Once I hit here, once I'm at this point, now I have a torque where the friction is pushing back. Now my torque diagram looks like this. So here's my axis of rotation. I'm rotating around the middle. There's my force of friction. You can also see that the normal force is pushing up this way, and the normal force is pushing here out at the end. And then gravity is pulling straight down. The only torque that's causing rotation, let me draw this free body diagram, this torque diagram better. So there's my center. The normal force is happening down here, but it's pointing that way. The force of gravity is pointing that way. And then the force of the push is going that way. Oops, force of the push, normal force, force of gravity. There we go. That lines up with that. Now I have friction there. Now I have a torque. The torque is not 0 anymore. So from C to D, there is a change in the this is problem 1, part B. So something about I need torques, I need external torques on the system. The only place so far that I've got a torque is from C to D. Back to here, there's just the normal force. Well, the normal force is happening down here, and the force of gravity is happening up there. But they're happening in different directions. There's no torque in the same thing out there. The only place where that torque is happening is out here. As far as question, how do you figure out the torque angle? So your torques are happening. Remember, you've got, I kind of wanted to grab this and slide it, but I can't. All right, what was there? Let's zoom into that ball. Where do I have space to do that? All right, let's zoom into that ball. The object, where is if it's going to be rotating, it's going to be rotating around its middle. So this is my axis here. So if we want to look at from A to B, we can draw the forces on where the things are happening. So if I draw from the axis to where the force is happening from the push is happening out here. So there's the force of the push. You guys can review this. Mostly erased. So torque is, according to the sheet, is RF sine theta. Oh, that's R cross F, which is RF sine theta, where theta is the angle between R and F. So, here the torque due to the push is going to be R. It's the radius of my circle. F, force of the push, and then sine of the angle between the force of the push and R. So my R points from the axis to where the force acts. From the axis to where the force acts. So here, R points that way, FP points that way. That's 180 degrees. Sine of 180 degrees is 0. Again, back to the normal force. Normal force acts down here. Here's my radius. So my R points down this way. The normal force points back up. That theta is also 180 degrees. The force of gravity is acting here at the center of mass, which is also the center of rotation. So you both have the radius is 0, so then it goes away as well. Same thing here, but now let's get to that part from C to D. Let's take a look at it at and I'm rotating, friction is happening. The force of friction is pushing this way. So remember, when we draw our free body diagram, this is what it is on the box. You have to place these somewhere on your object. Now the position is where it is really what you're looking for. So I take this my normal force is happening. I'm green. My normal force is happening here. Down here at the bottom. Normal force, and there's my friction, and then my force of gravity. My force of gravity is happening here. That doesn't change. Force of gravity doesn't change, but now I've got some friction that's in there. So now I have, the torque due to friction is going to be R. It's my radius of my circle. The force of friction, which is whatever it is. And then you can see my R goes this way. My force of friction goes that way. There's 90 degrees in between there. So Reba says, well, the torque is acting right. So oh, okay. So remember, you don't we know that that's non-zero because the force of friction is going to be whatever mu times the normal force turns out to be. This isn't right. It's an actual ball. Is has a value. The sine of 90 is 1. So that means this torque exists. If this torque exists, we know that it happens over time. That means the angular momentum is going to change. If you placed R somewhere else for the normal force, wouldn't the angle change? Yes, but that's not where the floor is touching. So, right, the floor is not touching over there or over there. The floor is touching there. Yeah, like up a cliff or if it runs into a wall. So yes, as far as the position of the normal force changes. Yeah, so if it starts to go up like that, and the ball is moving that way, or it goes into other things, yeah, stuff, it does change. All right. Let's see. Wow, that was part A and part B. How far did we get? Nice. Nice. The radius has, so Soros asks, the radius has to be where the force is acting. But because that's where it's touching the ball. Force of gravity does not happen at the radius. The force of gravity happens at the center of gravity. So the radius, because of it, and so the center of gravity and the center of mass are at the same place. The center, the radius at which the center, the gravity acts on is 0. So let me walk that through a little bit. All right, the ground is pushing at the ball at because we need to figure out where our axis of rotation of where it's happening around. So Tisha says when the ball courses the friction area, wouldn't there be 2 forces, one frictional? Inertia is not a force, so there's only frictional force. Inertia does not. That is the tendency of the object to keep moving, but that's not a force and doesn't fall under your free body diagram. Yeah. So remember that's what we learned. So our center of gravity is where the torque due to gravity acts. For small things, the center of gravity is at the center of mass. So as it is, this is rotating here. So the force, so the object is rotating around the center of mass. So his question was, but like the pre-existing force of the plunger. Yeah. That plunger only acts here. So we took that over here. There's my force of the plunger. My force of the plunger is also acting at R. The force of the plunger is acting out. Let's see, it's actually acting over here. So the force of the plunger is this way. It's acting at R, but the angle between R and the plunger is 0. No, 180 degrees, because the R is this way, and then the force of the plunger is that way. You go 180 degrees between them. All right, got about 10 minutes left-ish. Anything else that you have on there? Begin. Ben says hello. Hi. Probably know who you are. Okay, so then the FBD doesn't make sense because if there's only a force in the opposite direction, then why is the ball still moving? Oh, hi, Ben. Good to see you. Bent over. That's terrible. The opposite direction is the ball still moving. Be careful that you don't confuse moving with accelerating. So these are not the same. Going to the velocity changes. This is changing the velocity. This is changing the movement. So we are still moving in that way, but the speed at which we are moving is now less. So the speed is changing, but not the acceleration. I'm sorry, the acceleration is changing. We have an acceleration. Let me kind of work that out. It's still moving forward, but it's not moving forward at the speed that it was before. Does that help, Hatiksha? Nice. All right. The angular Yoshika's question is the angular momentum changing from A to B? No, there is no change. The idea is that it's sliding because it is pushing at the center of mass. If the ball is pushing, if that plunger is pushing up at the top or pushing slightly below, then you don't. Then it begins to rotate. Back when social distancing finally goes up, we can look at go shoot some pool, and so when you the ball, you will see the ball start to move as it goes slightly off the felt on the table. The ball will just move, and then the friction with the table starts to make it roll. If you hit it up at the top, you actually give it some rotational inertia. And so then when it hits another ball, it has leftover rotational inertia and will keep rolling forward. If you hit it farther down at the bottom, you actually give it a little bit of back rotation. So then when it hits, it rolls back. And that's why shooting pool is a skill. With that, I think we should end here out where we're going from there. And nice. Good job, team. Keep your eyes out. There's an announcement coming from the district here pretty soon if it's not already out there. Dylan said, ESU just said school will be out until May 1st. Yep, there you go. All right. Keep your eye on School Loop and we will figure it out. Nice. Good job, team. Remember, don't panic, and we'll figure some stuff out. Nice. And wash your hands. Don't touch your face.